I'm going to walk through the numerical solution to the following differential equation. D squared t dx squared plus t dt dx equals t plus x. And the boundary conditions given to us in the problem are t of 0 equals 10 and t prime of 0 equals 1. So we want a solution between x is between negative 10 and 10. So this is known as an initial value problem. I intentionally chose the domain to make it seem a little strange that it's an initial value problem. If I had said I want to solve for x going from 0 to 10, and I call it an initial value problem, it would probably make sense to you because I'm giving boundary conditions at x equals 0. But we are not just interested in x equals 0 plus 10, so it may seem odd that the boundary conditions are in the middle. It turns out that an initial value problem refers to a differential equation where the boundary conditions are sufficient to solve the problem, which I haven't yet shown you, and they occur at the same value of the independent variable. In this case, that value is 0. If we had boundary conditions at x equals 7, if we knew t and t prime at x equals 7, this would actually still be an initial value problem. And in order to understand that, I think we need to put this equation into standard form and briefly discuss how to solve it. So I'm not going to go into detail on the theory of solving differential equations numerically right now. I'm going to just say a few words about Euler's method, which is the simplest method of solving an initial value problem. And I'm going to convert this equation into standard form. And hopefully you'll be able to see why standard form and Euler's method go hand in hand. Let me start by saying, if I wanted to calculate y as a function of x, okay, and I'm not talking specifically about this problem. I know we're trying to solve t as a function of x, but any y as a function of x. And let's imagine that at some value of x, I knew the value of y, and I also knew the value of y prime. This is a slope, y prime. Well, you can use that information to extrapolate where y is going to be close to this value. Let's call this x0, and let's call this x1, and the distance between x0 and x1 is delta x. So y at x1 should be approximately equal to y at x0 plus y prime, the slope of the curve at x0, times delta x. Okay, so that is effectively saying that if you start at the first point and then you go in a straight line with a slope equal to y prime, you take a step delta x, and this would be a good approximation for y at x1. This is in fact Euler's method. And it's reasonably accurate, perhaps, as long as delta x is small enough. So what I'm trying to say here is that if we really want to calculate y as a function of x, then I need to be able to evaluate y and y prime at some starting point. And that's what we mean by an initial value problem. And by the way, I could also extrapolate backwards. I could have used y prime at x equals 0 to calculate y at some x that is actually earlier than x naught. So now we can talk about standard form. So standard form allows us to calculate y prime starting at the position of the boundary conditions, y and y prime that is. So let's look at standard form. So standard form looks like this. So standard form for a differential equation is going to look like y prime equals some function of x sub I and y sub I. And in fact, I think I could even say y prime at x sub I. So if I have a differential equation that has the form y prime, a single derivative, and that derivative can be computed if we know the position x and we know all the values of y. These are the dependent variables. You'll see what y is for this problem shortly. Then you can use Euler's method to solve this problem. So let me see if I can make that a little more clear. So this is not in standard form. So standard form does not allow second derivatives, and it does allow a first derivative, but it has to be isolated on the left-hand side. So let's convert this problem to standard form. So I'm going to define z as being dt dx. And what this means is that dz dx equals the second derivative with respect to, or of t with respect to x. And so this equation then becomes dz dx plus tz, remember dt dx is z, equals t plus x. And I can also say dz dx equals t plus x minus tz. So this equation is not sufficient because we started off with one thing that we wanted to calculate, one dependent variable, T, temperature perhaps, and then we invented Z, which also depends on X, but now we have two dependent variables, so we need a second equation. That second equation is already here, except let's just write it out. dt dx equals Z. So now if I define, so this is my system of differential equations. So now I can define y as being tz. So y is now a vector of dependent variables. They both depend on x, and I think you can agree that that this is standard form. Let me write it in vector form. So dy dx vector is going to be dt dx dz dx, and that's going to equal z t plus x minus tz. Okay, so now let's look where we're at with the boundary conditions. So this boundary condition can be translated because we know t prime is now z. So we know that y at x equals 0 is going to equal t is 10 and t prime is 1. 10, 1. Okay, so we know y at x equals 0, but we also can use that information to calculate y prime at x equals 0, because notice that t is 10 and z is 1, right? So y prime at x equals 0 would equal 1, and then 10 plus 0 minus 10 times 1 equals 1, 0. So now notice that I have y and I have y prime. And so if we did one step of Euler's method, let's just say delta x equals 0.1, then we can say that y at x equals 0.1 is approximately equal to 10(1) plus 0.1 times 1, 0. And that should equal 10.1 and 1. Assuming I did the math right, which is not a great assumption. So z is 1, and then t is 10 plus 0 minus 10 times 1. So yes, that does seem right. So what we're going to do in the next video is we are going to write a MATLAB program that keeps doing this over and over again, right? We'll choose a step size, and we will use Euler's method to calculate subsequent values of y. We have to go forward from 0 to get to 10, and we have to go backward from 0 to get to -10.